last 30 years, we've pioneered large-scale atomistic simulation on the cloud. For example, in 2012, we set a world record. It was the first and largest cloud computing study showing the power of large-scale virtual screening on the cloud. Shortly after that, we continued with another world record. In 2014, we broke the initial record, that first life science record, with a material science cloud-based computing record. We did a large-scale material science cloud computing project in collaboration with the University of Southern California. And this time, instead of classical simulation, we used quantum mechanics to screen the optoelectronic properties of over 200,000 molecules in 18 hours. And we've been doing that with our partners. And so here's an example just from 2020. Schrödinger and our users have followed these initial examples using cloud resource to execute massive screening projects. Here's an example that's been disclosed working with Panasonic Corporation in Japan. And I'll talk more about this in a few slides. In terms of application, there's different ways to look at it. Rather than classes of materials, we can look at individual applications. And here's a wide range of different application areas that we apply Schrödinger's material science technology toward. As I said before, all companies that need to select the right materials for making their product or design new chemicals and materials as products can benefit from a digital chemistry approach carried out at varying scale. So something about the cloud. So there's a lot of different vendors out there to work with. I mean, there's the big three. There's a lot of different companies that help you run simulations on the cloud. Schrödinger's material science platform integrates seamlessly with all of the major cloud resource providers. So just to talk about some details of our world record mega run that was done in 2013 and announced in 2014. So this was in collaboration with the Thomson Group at the University of Southern California. And so the problem we were looking to tackle was for organic solar cells, photovoltaics. That project finished in 18 hours. That represents 264 compute years. And the stats are here on the left. You can see that at the time it was a world record for computing. So this is a collaboration with Panasonic looking at using virtual screening on the cloud to identify new radio frequency ID materials. So here we need organic materials that can be inkjet printed and have high charge mobility. But what's really exciting is that we've used this now as a training set for machine learning. So in doing the initial physics exhaustive deterministic screening, we have some new material to go and investigate in the lab, but then we can train machine learn models to go and do inverse design and continue and find even more designs of materials that have the right property profile by using machine learning. So continuing on and getting away and sort of beyond single molecules and single input structures, we can think about reactivity. And continuing on, the previous examples looked at molecules and quantum mechanical calculations. We were really starting to differentiate capability and do new things when we pushed molecular dynamics onto the cloud at the mega scale. Each point on this plot on the left actually represents several hundred MD simulations. You have to equilibrate and converge at multiple temperatures, and then we do that for 10 replicates per polymer. And there's literally, so there's just an enormous amount of simulation that goes on to get this plot on the left. All in, there's more than 140,000 5-nanosecond NPT MD simulations executed on GPU cloud, and this represents the largest MD study to date. One of the key things that limits the application of AI and machine learning is the scarcity of data sets. Where do you get the training sets? Very often the experimental data sets don't exist, or there's not enough data, or they're of questionable quality. So one thing we can do is we can use physics at scale to generate training sets from which then we can build our ML models, which enables future of inverse design and forward-looking prospective ML prediction. Starting with this example here, this is a collaboration with SABIC Specialties. This is a project that we did together using ML for material selection for new polymers for a variety of different applications. Our partner SABIC had experimental data to build models from, so we were able to construct high accuracy ML models with which to virtually screen the design space for polymers with different property profiles for different applications. So moving from individual molecules in molecular materials to homocatalysts to polymers, the next thing is we want to talk about formulations. And this is where we're going to demonstrate leveraging physics-based simulation to get training sets to do cutting-edge machine learning for formulations. So to have something with a high boiling temperature and a low viscosity, that's a difficult problem. And so what we had done is we did physics simulations of viscosity and boiling temperature. We fit forward-looking ML models, and then we did inverse design. We had a prior agent. We basically had one neural net predicting new material, and we had a scorer. And with every iteration, it updates the weights so that it's learning how to predict matter with the right property profile of low viscosity, low boiling temperature. And so you can see in the inset, there's a molecule there. This was not available commercially. This is one of the molecules we identified in this work. Panasonic synthesized this and then characterized it. And the agreement with our ML models was just truly outstanding. So there's different ways that you can work with Schrödinger. So in summary, we have 30 years of innovation. Schrödinger is the industry leader for atomic scale simulation and machine learning for materials discovery and optimization. At all levels of adoption, digital chemistry has a transformative impact. And going to the cloud provides limitless on-demand resources, basically, which really changes how simulation can be used.